This is lecture 5A, and we're starting the chapter on gas laws. I want to introduce some measurable properties of gases first. When you collect a gas in lab, some of the things we're going to want to know about the gas is first the quantity of the gas. Quantity of gas is represented by the letter N, and it's measured by the number of gas molecules, or on a macroscopic scale, the number of moles of gas present in the container. We call that the quantity of gas. Another measurable property of a gas is its pressure. That's going to be designated by a lowercase p, and that's measured usually in millimeters of mercury. It's technically defined as the height of a mercury column at 0 degrees Celsius, but pressure can also be measured in the units of torr, atmospheres, and pascals, which we'll discuss later. We can also measure the temperature of a gas. Temperature is abbreviated by capital T. Lowercase t is usually used in science to represent time, so capital T for temperature. We have thermometers that measure temperatures in degrees Celsius, but we'll see for a lot of our mathematical calculations involving gases, we're going to want to have the temperature measured in the Kelvin temperature scale instead. And then finally, something else we can measure about gases is their volume. We use capital V to represent volume. Lowercase v is often used for velocity, so capital V for volume. And we can measure a gas's volume in any volume unit like liters or milliliters. So of these four quantities, the first one, quantity of gas, it's just a measure of the number of molecules, or if it's an atomic gas like a noble gas, the number of atoms that you happen to have in a sample. And over the years, there have been relationships worked out as to how some of these different quantities, quantity of a gas, for example, is related to the volume of the gas in the container. And the relationship between the volume of a gas and the quantity of a gas was first expressed by Amedeo Avogadro, and that's called Avogadro's law. It's the volume of a gas is directly proportional to the quantity of gas, provided the pressure and the temperature of the gas do not change. That last bit of this definition is fairly important scientifically speaking. If you wind up doing, or if you have done any type of science project in the past, maybe in junior high school, your job was to figure out or answer the question, will plants grow in the dark? The way you do a scientific experiment is you take a plant and you put it maybe in a dark closet, but you have a control plant that you put out in the backyard. And you observe the two plants for over a couple of week period, and then you look and see, did the plant that was in the dark die, but the one that didn't have darkness, did that live? Now, that's going to be an accurate scientific evaluation as long as you don't change any other variables. For example, if the plant you put in the backyard, you water every day, but the plant you put in the closet you didn't water, and it wound up dying, did it die because of lack of light, or did it die because of lack of water? You had too many variables. So when we're testing particular properties, we want to make sure every other variable is held constant. So this last part of this definition says, provided the pressure and temperature of the gas do not change, holding those constants, Avogadro, who was a fine-looking man, showed that the volume of a gas is directly proportional to the quantity of gas. If we want to write that algebraically, we would say volume is proportional to the quantity. That little symbol there is a proportionality sign, which there is a chance you may have seen it back in your geometry days when you're doing similar triangles. They use that to represent triangles being similar as well. Now, in science, we don't use a whole lot of equations that have proportionalities in them. We have equations that have equal signs in them. But I can't just erase the proportionality sign and put an equal sign because volume doesn't equal quantity. 3 liters doesn't equal 2 moles. So whenever we take out a proportionality sign and we replace it with an equal sign, we have to include a constant in the equation. And so if we rewrite Avogadro's law as an equality instead of a proportion, I would say V equals K times N. You may remember this from earlier in the semester, but this is an equation that has variables on both the left and the right side of the equation. The V is on the left, the N is on the right. And when those variables are on opposite sides of the equation, that means those properties are directly proportional. So as N, the amount of gas in a container goes up and up and up, and you might consider a balloon. What if you blow a lot of air molecules into the balloon? What happens to the volume of the balloon? It gets bigger. So N and V are directly proportional, and mathematically, if you just look at an equation and you see that two variables are both in the numerator but on opposite sides of the equation, then that means they are directly proportional. If one gets bigger, the other gets bigger. If one gets smaller, the other gets smaller. So this is Avogadro's law. You've heard of Avogadro before because they have that number named after him. The number of atoms or molecules in a mole is named after Avogadro. He didn't discover the number, he didn't invent the number, but he did some pivotal work early on in terms of chemistry. Let me show you something that he did that was actually really significant, and this is why they actually named the number after them. A couple labs ago, you took liquid water, you put a couple of electrodes in it, you attached a battery to it, and the water bubbled and produced two different gases. And you should have noticed that there was a lot bigger volume of one gas than the other. In fact, their volume ratio should have been exactly 2-to-1. And Avogadro had done reactions like this, and he had realized that as well. And he said, I think I know what's happening. If you take water and you pass an electric current through it, you're decomposing it into hydrogen and oxygen. And if I write a balanced equation, I'm going to get 2 hydrogens to every 1 oxygen. And Avogadro made the supposition that if you have twice the number of hydrogens as you do oxygens, then in the gaseous state, its volume will be twice as big. So he was saying that if you take maybe, I don't know, 4 water molecules and you decompose them, you'll get 4 oxygen atoms and 8 hydrogen atoms. And because the number of hydrogen atoms is twice as big, you're going to have twice the volume. That was really significant. People started believing, okay, when we collect gases, the volume is directly proportional to the number of moles or the number of molecules. So if we have a ratio of 1-to-2, that means we have to have twice as many molecules in the volume of 2 as we do in the volume of 1. Now, let's turn this reaction around. Let's take hydrogen and oxygen and see if we can react them to form water and see what we think would happen. So the reaction reversed would be 2H plus O yields H2O. So if I wanted to write a stoichiometric reaction for this, where the ratios in the balanced equation match the number of atoms I actually use, I would need to take 2 volumes of hydrogen and 1 volume of oxygen, because that would give me double the number of hydrogen atoms as oxygen atoms. So here I've got 4 oxygen atoms in the 1 little volume, and to make water, I would want to have double the volume, so I would have 8 hydrogen atoms. These would combine to make 4 water molecules. And if you're creating them in the gaseous state, they're going to form a certain amount of volume. And because it's only 4 water molecules, it should be 1 volume. And this is what scientists predicted at the time. When they actually did this experiment, you didn't get 1 volume of water vapor. You got 2 volumes of water vapor. And people couldn't understand why that was, because if there were 2 volumes of water, that means the balanced equation would have had to have a 2 in front of the H2O. And instead of forming 4 water molecules, you had to be forming 8. Well, that mystery was solved by Stanislaw Cannizzaro, who looked at this reaction using Avogadro's principle that equal volumes contain equal numbers of molecules. So double the volume would have double the number of molecules. He said, I can figure out why this isn't working. We're wrong in thinking that hydrogen and oxygen are atomic substances. What if they were really diatomic molecules? If they were, now I would have 8 diatomic hydrogens with 4 diatomic oxygens. That would be enough O's and H's to form 8 water molecules. That's why we get 2 volumes. This is the original reason why we believe the elements of hydrogen and oxygen are diatomic, because they satisfy Avogadro's principle that equal volumes of gases contain equal numbers of molecules. So quantity of gas, the first property. Second property I want to talk about is pressure. If you've had some physics, pressure is actually a force that an object exerts per unit area. So gas is in a closed container. The gas molecules are moving in straight line motion, and they're colliding with the inside surface of their container. The force of those molecules hitting the inside walls of the container, and if you divide that by the area of the inside walls of the container, will give you the gas's pressure. So gases in a closed container, because they're constantly colliding or bombarding with the inside walls, they're creating a force every time they hit, and they're creating a pressure. So the pressure is due to the constant bombardment of the inside walls of the container by the gas molecules. Now, what we've decided to do is we've decided to give a name to typical atmospheric pressure on the planet Earth at sea level on a lovely spring day. We call that standard pressure. So if anybody ever refers to something under standard pressure conditions, that means the pressure of the gas is normal atmospheric pressure. Normal atmospheric pressure is 760.0 millimeters of mercury, which means in a mercury barometer, the atmosphere would support a column of mercury 760.0 millimeters high. Technically, that's when the mercury is at 0 degrees. If the mercury were to warm up, it would expand and you'd have a slightly higher column. So anytime somebody reads a mercury barometer and it's not at 0 degrees Celsius, they actually correct it back to what the height in millimeters would be if it was at 0 degrees. And that's how we get our units of pressure. Now, at some point, people thought, I don't really want to have a pressure unit look like you're measuring the length of something. So they just decided to make a definition. They were going to call 1 millimeter of mercury pressure at 0 degrees Celsius a torr, after Torricelli, who was the scientist that invented the barometer. And so therefore, standard pressure is also written as 760.0 torr. If you want to have a larger unit of pressure, they've decided that standard pressure we're going to call 1 atmosphere's worth of pressure. And so standard pressure is also exactly 1.000 atmospheres, or ATMs. The actual SI unit, or the metric system unit for pressure, is actually the Pascal. And if you want to know what standard pressure is in pascals, it'd be 101,325 pascals. That last number, I'm not going to expect you to know. You could look that up whenever you need to. But I would like you to know the top 3 so that and understand they're all equated to each other. 760.0 millimeters of mercury equals 760.0 torr equals 1.00 atmospheres. And by knowing that, you should be able to convert between the top 3. The bottom one, if you just need to get to pascals, just look up the value. Now, as the entire world moves towards a completely metric-based system of units, at some point, they're going to actually redefine standard pressure. And when they do that, they're going to make standard pressure equal to a nice, clean number that's not going to be 101,325 pascals. It's going to be redefined as 100,000 pascals, because Pascal is actually the SI unit, or the metric system unit. So eventually, atmospheres, torrs, and millimeters of mercury may go away. So if we do that, standard pressure will be defined as 100,000 pascals, which means that standard pressure will be 0.9896 atmospheres, or 750.1 torr, or 750.1 millimeters of mercury. But they're not doing it now. You don't need to know that for this class, but let me warn you, in 15 or 20 years, when your kids come home from chemistry in high school and they ask you, hey, what's a standard pressure? And you go, oh, it's a 760 torr. They'll go, it's not, it's 750.1. And I don't want you to think back that I taught you wrong all those years in the past. It was actually correct at the time, but in the future, it may be 750.1. Now, pressure can be related to the volume of a gas, and that relationship was first quantified by Robert Boyle, and this is called Boyle's law. The volume of a gas is inversely proportional to its pressure, and then our proviso, provided the temperature and the quantity of the gas do not change. I think we open up the entire semester by the first day talking about Robert Boyle, and here he comes again talking about a relationship between gas volumes and pressures. Boyle was half Irish, half English, and if you ever wind up going to Ireland, you wind up going to Dublin, of course you're going to go there so you can go have dinner in one of the little pubs and have Irish stew and fish and chips and corned beef and cabbage and maybe a Guinness or so. But if you do wind up going there, you really should go to St. Patrick's Cathedral. St. Patrick's Cathedral was built 800 years ago, but a significant damage was done to it. And it was actually rebuilt in the 1600s to a large extent. And one of the benefactors to that, for that, was Robert Boyle's father. And so Robert Boyle's father now has a mausoleum, a little area of the church inside of there dedicated to him and his wife. And it looks like this over here on the left side, where that's supposed to be him and his wife laying to rest at the very top. At the very bottom of that is a little statue of a little boy, and I've blown up the picture on the right side, and that's a statue of Robert Boyle. So if you're going to do a chemistry pilgrimage to Ireland, then you have to go to St. Patrick so you can visit the little statue there of Robert Boyle. But that's really not related to what we're doing today, is it? So Boyle's law says that the volume of a gas is inversely proportional to its pressure. So if I want to write a proportionality equation for that, instead of saying V is proportional to P, because that would be a direct proportion, I say V is proportional to 1 over P. That's how we show that values are inversely related. If I want to make this an equality statement, I'll take out the proportionality sign, replace it with an equal sign and a constant, and the equation becomes V equals K over P. Or if you don't like denominators, multiply both sides of the equation by P, and you get PV equals K. This is an equation where the two variables, the P and the V, are both in the numerator on the same side of the equal sign. They always multiply to make the same constant. So that means if P gets bigger and bigger and bigger, V has to get smaller and smaller and smaller. This is how you recognize algebraically the two variables are inversely related. They multiply by each other, both in the numerator, on the same side of an equation. And this inverse relationship means that as the pressure increases on a gas, as you put more little green weights on it to compress that gas so it puts it at a higher pressure, you make its volume get smaller. So as the pressure gets higher, the volume gets smaller, or the other way around. As the pressure gets lower, the volume would get higher. Now, the atmosphere on our planet is a gas, and if we want to measure the pressure of the atmosphere on Earth, we use a device called a barometer. A barometer is essentially a beaker of mercury, and then a long glass tube completely filled with mercury, and that tube turned upside down and set into the beaker and then supported. So I have a dish of mercury here, my long tube of mercury, and that tube of mercury used to be completely filled. But what happens is the mercury will start draining out, and then eventually it'll stop draining and it'll reach some level. And the level that you see right here, this measured difference between that level and the level in the open beaker or the open dish is what we say is atmospheric pressure. Now, some facts about barometers, okay? First, it doesn't matter how thick that glass tube is that you're putting in the inverted beaker. So the pressure of a gas that's measured with a barometer is proportional to the height of the mercury column, but not to the diameter of the mercury column. And if you're a fan of mathematics, let me show you why that is, okay? Look at the picture on the left. The surface of the mercury I'm going to color in blue right now. This is where all the molecules in the atmosphere are hitting the mercury in that open dish. The force of those molecules are hitting the mercury and they're holding up mercury atoms in that column. This is what's causing that to happen. So the atmospheric pressure is going to be equal to the force of the atmospheric atoms hitting over that blue surface area. So the atoms are striking the mercury. They're striking it all along this blue colored area here. And so the pressure would be defined as the force of the collisions of those atoms from the atmosphere over the area that the atmosphere is hitting on the mercury, okay? Now, look at this little blue section right here. This is the area that all the mercury in this column is pushing down on in the beaker, that little area right there, okay? So the pressure of the atmosphere must also equal the force of all the mercury atoms in that long column pushing down on that small little area of mercury in the column. Why do they have to be equal? Because the column of mercury is stationary. There's an equilibrium. The forces must be equal. The force of the atmosphere pushing on the mercury on the outside is exactly equal to the force of the mercury atoms pushing on the surface on the inside of that very thin tube. So we can say the force of the atmosphere divided by the area that the atmosphere is pushing on must equal the force of the mercury in its column divided by the area that the mercury in its column is pushing on. Now from physics, since force equals mass times acceleration, or in Earth's gravitational field, acceleration is called the gravitational constant of Earth. Force equals m times g, that's Earth's gravitational constant. I can substitute the force of the mercury in the column by mass of mercury times the gravitational constant g. So now our pressure of the atmosphere equals the mass of mercury multiplied by the Earth's gravitational constant divided by that little area that's still colored in blue in the picture that the mercury is pushing on. Second, we know that density equals mass over volume. So if I want to solve this for mass, I can say the mass of any material is going to be its volume times its density. And in our little green equation over here, I've got the mass of mercury written, so I'm going to replace mass of mercury with its volume times its density. So therefore, the pressure of the atmosphere is going to equal the volume of the mercury that's in that long column, multiplied by the density of the mercury, multiplied by the Earth's gravitational constant, divided by that blue little area that the mercury is pushing on the surface of the liquid that we have at the bottom of that tube. Okay? Now, volume of the column. How do we calculate the volume of mercury in that long, thin tube? That's a cylinder. How do you get the volume of a cylinder? The volume of the cylinder is the height of the cylinder multiplied by the area of the circle on either edge of the circle. So the volume of the cylinder equals height, how tall it is, in this case it's 760 millimeters, multiplied by A, which is the area of that blue little circle at the bottom, and then technically the blue little circle on the top. So if I replace my volume with H times A, then finally the pressure of the atmosphere when you use a barometer will equal the height of the mercury column multiplied by the area the mercury is pushing on the bottom of the tube, multiplied by the density of mercury, multiplied by Earth's gravitational constant, divided by the area of the mercury pushing on the bottom of the tube. And if you can see, the areas cancel out. What does that mean? It means the size, the diameter of the tube doesn't make any difference because the pressure is just proportional to the height of the column multiplied by a pair of constants, density and Earth's gravitational attraction. So if you make a barometer, you would probably use the thinnest glass tube possible because mercury is dangerous and expensive. You wouldn't want to make a really thick, big tube because you'd have to use a whole lot of mercury. Okay? So that's one fact about a barometer, that if it's used to measure the pressure, doesn't matter how thick or how thin the column is that you have supported in that big container of mercury. Second thing, you don't have to use mercury to make a barometer. Barometers can be made with any liquids. But if you use a less dense liquid, that means that the atmospheric pressure is going to be able to hold up a column of that liquid way higher. And that's because what the atmosphere is doing is it pushes on these mercury in the open container, is it's holding up a certain mass of liquid. So it's going to hold up a certain mass of mercury if you have a mercury barometer. But if you have a water barometer, it's going to hold up the same mass of water. And because water isn't as dense, it's going to have a lot bigger volume. So the column height will be way higher. So if we have a mercury column that's 760 millimeters high, I know that the pressure of 1 millimeter of mercury would be equivalent to 13.6 millimeters of water. If you're supporting 1 millimeter height of mercury, because water is so much less dense than mercury, you can actually hold up a column of water that's 13.6 millimeters high. So if I convert from millimeters of mercury to millimeters of water to figure out how high would my column be if I had a water barometer instead of a mercury barometer, that comes out 10,300 millimeters, which I don't know what that means, but it's about 34 feet. So we could make a barometer out of water, but we would need a 3-story. We could actually do it in our new sciences building, right? We put it down on the first floor and the barometer would go all the way up to the 3rd floor. And then we could be on the 3rd floor balcony there and read what the barometric pressure is for the day. But that's so inconvenient. Nobody actually uses water to make barometers. That's why they use mercury, so you can actually keep it in a regular sized room. Now, how did I get that number? 13.6 millimeters of water equals 1 millimeter of mercury. Let me show you where that came from, okay? For a mercury barometer, the atmospheric pressure we know is the force of the atmosphere over the atmosphere area that it's pushing on in the open beaker. And if we use mercury in a barometer, then that's going to equal the force of the mercury divided by the area that the mercury is pushing on. They have to be equal because you have an equilibrium, equal forces between the atmosphere and the mercury. And that force is m times g. And so that means the mass of mercury times the gravitational attraction over the area of the mercury that's being pushed on the surface of the liquid is going to equal the atmospheric pressure. If you have a water barometer, it has to be the same thing, only it's going to be with water instead of mercury. So the atmospheric pressure is going to be the force exerted by the water molecules in the tall column on the area that the water molecules are pushing, the very bottom of the tube, on that open container. And if I just replace the force of water by mg, therefore the mass of water times Earth's gravitational attraction over the area is going to be the atmospheric pressure. So these last two statements have to be equal to each other because they would both measure atmospheric pressure. So if they both measure atmospheric pressure and we cancel out the Earth's gravitational constants because they would be the same, and if we're using tubes that have the exact same diameter, then the areas would be the same. This is what must be true when you use a barometer of varying liquids to measure atmospheric pressure. The atmospheric pressure holds up a specific mass of mercury. It would hold up the exact same mass of water. So in your columns that are being supported by the atmosphere, the gas would support equal masses of any liquid. So in a glass tube of constant diameter, which would mean A would be constant, the gas will support equal masses of any liquid. So let's say we have a gas and it's supporting 13.6 grams of mercury. If I made a barometer out of water, it would support 13.6 grams of water. So we know the masses would be the same, but what would be the volumes? If we want to figure out the volume of mercury that would be supported, we're going to use mercury's density, which happens to be 13.6 grams per milliliter. So if we know mercury's density, I can use that as a conversion factor between grams and milliliters. I'll arrange it upside down so the grams cancel out. And if I multiply this out, that means that if you're holding up 13.6 grams of mercury, the amount of volume that's being held up is 1 milliliter. Let's do the same thing with water. If we use a water barometer to measure a pressure and the atmosphere is going to be holding up the same mass of water as mercury because it half would be the same, if I use water's density, which is 1.00 grams per milliliter, let me convert the mass of the 13.6 grams of water into volume and see how much volume of water would be supported by the exact same atmosphere. So using the density of water, I get 13.6 milliliters. So you can see that you're always going to hold up 13.6 times more water than you will mercury because 13.6 is 13.6 times greater than 1. And because the area of the tube is going to be constant because we use the same tube for both either water or mercury, then that means the amount of volume that's being held up in each of those columns is only going to be proportional to the height. And so if you have 13.6 times more volume of water supported than mercury, you will have a height in your tube that's 13.6 times more for water than mercury. So therefore, 13.6 millimeters of water would have to equal 1, or millimeters of water in height would have to equal 1 millimeter of mercury in height. Now, the simple way to get that number is, notice what the densities were. They're 13.6 for mercury and 1 for water. Because mercury is more dense, you're going to hold up a smaller volume. Because water is less dense, you're going to hold up a bigger volume. It'll always work out that if you just flip the densities, that's going to tell you the volume or the millimeters that each particular liquid will support that'll be equal to each other. So 13.6 millimeters of the less dense water will be the same as 1 millimeter of the more dense mercury. Now, if you have a gas that isn't atmospheric pressure, but maybe it's a gas that's just collected in a bulb in your lab or something, and you want to measure its pressure, we use a manometer to measure trapped gases. And a manometer actually is a tube that's usually filled with mercury, and we used to call it a U-tube, but now if I were to say that, you would be confused because you think I'm talking about a website, right? So I'll call it a J-tube instead, so you're not confused. So if you take a gas in a container in lab and you hook that gas up to a J-tube that has mercury in it, then we can use this device, it's called a manometer, to figure out what the pressure of the gas is. And the important reading on a manometer is the difference in the levels of the liquid on the side that's exposed to the gas, which is right here, and the side that's not exposed to the gas, which is up here. I've measured the difference in levels as 125 millimeters. Now, how do we use that 125? That shows you how the gas's pressure compares to whatever the pressure is on the opposite side. In this case, I have what's called a closed-ended manometer. A closed-ended manometer does not allow any gas inside the manometer on the right side. That means on the right side, you have a vacuum. And the pressure of a vacuum is 0 because there's no gas in there to hit the walls to exert a pressure. So when you look at a manometer, whichever mercury level is being pushed down further, that means the gas on that side has the higher pressure. So our gas must have a higher pressure than the vacuum because look at this. This level is lower than this level, right? So the lower pressure is the lower level is the one that has the gas pushing down harder on it. So our gas has a higher pressure than the vacuum, and the difference in levels tells you how much higher. It's 125 millimeters higher. And in fact, it's 125 millimeters higher than 0. So you just go 0 plus 125, and that will be the pressure of our gas measured in millimeters of the liquid that's in the J tube, which in this case is mercury. I've made it silver because mercury is silver. I used to make it red because I used to think mercury was red, but that was wrong. Thermometers that have red stuff in it, that's really not mercury. That's just alcohol with red food coloring in it. So I was a little late on the uptake of that. So I've got this picture accurately. This says mercury is silver. There's a lot of things I wasn't clear upon when I was younger. When I was starting second grade, I remember the first day I walked into my second grade classroom, I looked around and go, what are all these people doing here? Because they were in my first grade class the year before, and I figured I was going to be going into second grade, so I'd be with all the second graders now. And that's when I realized everybody else gets to go to second grade also. Wasn't clear on that concept. Let's try this manometer. This is a different manometer. This one, notice on the right side, it's open-ended. If you have an open-ended manometer, that means there's not a vacuum on the right side. That means the atmosphere sends its molecules in, and the molecules now start hitting the mercury here on the right side. So the pressure on the right side of the mercury column is 765 millimeters. Our gas is pushing here, and we want to figure out what the gas's pressure is. And the important measurement in a manometer is the difference in the levels. The difference in the levels on the left and the right is 125. So that means the gas's pressure and the atmosphere's pressure are 125 different from each other. And the way you figure out which one is higher is you see which one is pushing its mercury down more. And our gas is pushing its mercury down way more than the atmosphere is. So that means the gas's pressure must be higher than the atmosphere's. And in fact, it'll be 125 millimeters more than the 765. So you add those together, you'll get the pressure of the gas in this open-ended manometer. So they're essentially read the same way, but you just have to understand what is the pressure on the right side. A closed-ended manometer, it's going to be 0, but an open-ended manometer, it's going to wind up equaling whatever the atmospheric pressure is on that particular day because the atmospheric pressure is always changing. It's not ever the same for an extended period of time. Now, if I wanted to make a manometer with water instead, perfectly fine. If you look at this picture, this is a closed-ended manometer, and we have a vacuum on the right side, which means the pressure on the right side is 0. Our gas is pushing down on the water more than the vacuum is, so it has to have a higher pressure than the vacuum. So if we wanted to say what the pressure of the gas was, we would say it's the difference in levels added to 0. So 54 millimeters greater than 0. But because this is a water manometer, the pressure of the gas is 54 millimeters of water more than 0. You could say the pressure is 54 millimeters of water, that's fine, but it's not a common unit of pressure. A common unit of pressure is millimeters of mercury. So if you're using a barometer with a different liquid, like say water, if you figure out what the pressure of the gas is, you're going to have to convert that into what it would be if it were mercury instead of water. So what I'm going to do is I'm going to go, I wonder what that 54 millimeter difference would be if it was mercury instead of water. So I'm going to do a conversion for the 54 millimeters of water difference into mercury. And that's the conversion factor we talked about before. 1 millimeter of mercury would be equivalent to 13.6 millimeters of water. So if I use that equality statement, I can figure out what the difference in levels would be if the liquid in the J tube was mercury instead of water. This comes out 4.0 millimeters of mercury. So if this was a mercury manometer, that just means that the gas's pressure would be 4.0 millimeters of mercury more than zero. And so the pressure would be 4.0 millimeters of mercury, to put it in a unit that's recognized by other people. If we have one more example of a manometer here, this one's an open-ended manometer. So now 765 millimeters of mercury is pushing on the right side. Our gas is pushing on the left side. I want you to notice something different about this one. The level of the water on the gas side is higher than the level of the water on the atmosphere side. That means the atmosphere's pressure is higher. So therefore, the pressure of the gas is going to be less than the atmospheric pressure. So in a situation like this, you would take the atmospheric pressure and you would subtract the difference in the levels. Now, the atmospheric pressure is 765 millimeters of mercury, but the difference in levels is 27 millimeters of water. They aren't the same units. You can't subtract 27 millimeters of water from 765 millimeters of mercury. In the old days, if you would ever go down to Tijuana, across the border, San Diego, and walk around the streets there, you could get your picture taken with a zebra, because they paint donkeys with black and white stripes there to make them look like zebras, and you can, as a tourist, get your picture taken with one. And if they ask you to pay, and you say, how much is it? And they say 10 pesos, and you give them a $20 bill, they're not going to go $20 minus 10 pesos equals $10 pesos. You can't subtract units that are the same. If you want to pay them, you've got to know what the price is in a particular unit, either peso or dollar, and then give them the amount of money in that same unit, right? So if you're going to subtract these two values here, we have to make the units the same. So first, realize that the pressure of the gas is less than the pressure of the 765 on the right side, because the level of water is higher on the gas side, it's lower on the atmosphere side. So it's 27 millimeters of water less than 765 millimeters of mercury. So we're going to switch the millimeters of water into millimeters of mercury with our conversion factor. And if we do this, we're going to calculate what the difference in the water levels would be if it was mercury instead of water. That comes out 2.0. So the picture really means that the gas is 2.0 millimeters of mercury less than the atmosphere's pressure of 765. That means the pressure of the gas is 763. Last thing I want to talk about today is graphing experimental data. Scientific relationships, if you ever publish them in papers, or if you're going to do projects in Bio 3A or 3B and make posters around the school, and you have to graph a numerical relationship, scientific papers and relationships are always expressed in linear form because they're easier to read than curves. There's less subjectivity in them. If the points of a experiment are supposed to be in a line, you can definitely tell if the data is good or bad, whether they lie in a line or not. We've seen that when we use Logger Pro and we've tried to do calibration curves, and you got an R-squared value of 0.99, your points are pretty much in a good line. But if a graph is a curve, there's a lot of subjectivity into that. Is that curve a good data? Is it bad data? It's kind of hard to tell. So whenever you graph things, you actually want to graph them so they become a linear relationship. And that means, going back to Algebra 1, graphing them in the form of y equals mx plus b. So the graph you'd want to make is you would want to place whatever's on the x-axis in this part of the mathematical equation, and then whatever's on the right side would be plotted on the y-axis of the chemical equation, or not the chemical equation, but of the plot. So let's talk about one of the relationships we discussed concerning gases today, because it turns out that it would not naturally plot as a straight line. And that's Boyle's law. Volume is inversely proportional to pressure. We could write V equals K over P, or I could write PV equals K, either way. If I ask you what kind of relationship is this, looking at the equation on the right, I find it easier to see there. The two variables multiply by each other to make a constant. That means they're inversely related. If I asked you how would that graph, you may or may not know that, but if you actually graph any inverse relationship, the graph turns out to be a hyperbola, which means if I graph volume on the y-axis and pressure on the x-axis, I would actually wind up getting a graph that asymptotically approaches the x and y axes. This is what you get when you have an inverse relationship. So if you were Robert Boyle and you were writing a paper on volume and pressure and you wanted to make a graph of your experimental data, you're not going to graph pressure and volume like this because it doesn't come out a straight line. So I'm going to show you 3 different ways that you can take data that looks like it should be hyperbolic or inverse and figure out a way to graph it so that it comes out as a line instead of a hyperbola. First technique, if you want to make a volume and pressure graph as a line, you can plot the relationship in logarithmic form. So let's take Boyle's law, V equals K over P. To plot logarithms, what you need to do to this equation is just take the logarithm of both the left and the right side of the equation. So the logarithm of the left side would be log of V, and the base 10 logarithm of the right side would be log of K over P. So I'm just making a logarithmic equation. With the rule of logs, I can simplify the right side of the equation because the log of K over P equals log of K minus log of P, if you remember that. This is just incidentally why logarithms were invented. In the old days, if they wanted to divide K by P, and let's say K was 4,932 and P was 647, well, guess what? There were no calculators and an abacus couldn't do that. They had to do it longhand. So somebody realized that if you take logarithms of numbers, which are just exponents, so the log of K is an exponent, the log of P is an exponent, then how do you divide exponents? You subtract them. So if you calculate the logs of the 2 numbers, all you have to do is subtract their logs, and then you'll be able to get the answer to your problem without doing a long division. Anyway, that's why they were invented. So if you take this equation, I'm going to move around the 2 terms on the right side of the equation. I'm going to put the negative log of P first and the positive log of K second, just switching them around. I want you to think about why I did that. If you look at this equation now and look where V and P are, they're in the positions of Y and X in Y equals mx plus B. But it's not just V that's in the position of Y, and it's not just P that's in the position of X. It's log of V is in the position of Y, the negative sign is in the position of M, that's your slope, log of P is in the position of X, and then log of K is actually in the position of B. So that means if you graph log of V on the y-axis, you're going to make a line that has a slope of -1, as long as you're graphing the log of P on the x-axis, and then it's going to actually cross the y-axis somewhere. It's going to cross the y-axis at the log of K. So this particular graph of log of V versus log of P will have a -1 slope. It'll cross the y-axis at log of P, but it'll make a straight line. So in your homework coming up for this particular unit, I'm going to have you graph data like P and V, and you're going to get a hyperbola. Then I'm going to ask you to graph log of P versus log of V, and I want you to see if it comes out a line or not. And I want you to actually practice graphing, because on your 5th test, you're going to have graph paper given to you, and I'm going to make you make graphs, and I'm going to want to see if you can take something like a hyperbolic relationship like pressure and volume and graph it for me so that it comes out a straight line. So this is one of the 3 ways you can do that. The second way you can make inverse data plot linearly is to plot the reciprocal of one of the 2 variables. So if I take Boyle's law again, and let me just take the right side of this equation and break it up into its 2 factors. One factor is K, and what's K being multiplied by? 1 over P. So the right side of the equation can be K times 1 over P. If you look at this, the V is in the position of Y in Y equals mx plus B. K is the slope. 1 over P is in the place of X. And what's our B value? 0. So if you plot volume on the y-axis, the slope will wind up being K as long as you plot the reciprocal of P on the x-axis, and you're going to go right through the origin where the intercept's going to be 0. So if I graph V versus 1 over P, I'm going to have a straight line with a positive slope because K has to be a positive number. It's going to cross exactly the origin, and all the points will lie in a perfectly straight line. So this is a second way to make inverse data graph linearly. The final way is to plot the product of the variables on one axis versus one of the variables on the other. So whenever you're doing something like this, it's really important to ask, why would they be doing that? What does the product of the variables actually equal? Because if we're doing pressure and volume data, They're saying multiply pressure and volume together and put that on the y or the x-axis. Why would they do that? Well, take Boyle's law and figure out what P times V equals. So let me put the P over to the left side of the equation, and P times V equals K. Why would that be significant? Well, that means if you make a graph where you're plotting PV on the y-axis, the PV value will always be the same number. So P times V plotted on the y-axis is a constant. It'll always be the same value. So when you graph that, every single y value will be the same number. So as you vary your volume on the x-axis, you'll always have the same product of pressure times volume. And that's the third way in which you can make inverse data graph as a straight line.